Hello, this lecture will cover pages 100 through page 108 of my lecture notes, so please print out those pages and have them in front of you as I present this lecture on combinational logic circuits, part C, using Karnaugh Maps to simplify logic equations. Karnaugh Maps, sometimes referred to as K-Maps, and if you look on page 100, at the top, the first thing I'm going to do is mention this combinational logic design procedure. It's very important as we go through the next week or so. We're going to do some design, and the design is going to center around combinational logic circuits. The second half of the semester we talk about sequential logic design, but the first half of the semester we concentrate on the combinational logic procedure. This is your procedure. Let me go through it real quick. You're going to get to know it very well, and you're allowed to have it out in front of you when we take the exam. Number one, you start with the specification. The specification is a detailed document that describes how the logic circuit should function. Sometimes it's one page, sometimes it's hundreds of pages, depending upon the work you're doing for the client and how detailed they want to describe their requirements for you. Drawing the truth table from the specification, that's your second step. You draw the truth table from the spec, showing the fundamental products for valid output conditions, just like we did in the previous examples and homework. You can use the sum of products form to write the Boolean expression for the output variable. However, I recommend from here on out the midterm form. And we're pretty much done with Boolean algebra. You'll be working with the midterm forms from here on out. You simplify the Boolean expressions for the output variable one of two ways. You can use Boolean algebra or you can use K-Maps. From here on out, we're using the K-Maps. And number 5, you realize the circuit. In other words, you draw the logic diagram or the logic circuit showing the inputs and the outputs. I want you to take a little bit of time and look over example 4.8 and 4.9. They're in page 140 and 141 in your textbook. I'll show you the problems here. Page 140, example 4.8 looks like that. And on the next page, example 4.9 looks like that. So if you have a different edition, that's what I'd like you to look over. Make sure you understand those problems. K-Maps, Karnaugh Maps. Let's talk about the K-Maps and how you use them. Most engineers do not simplify Boolean expressions with algebra. It's much easier to use K-Maps when you have 3, 4, or 5 variables or inputs. Logical expressions with 6 or more variables are best done by a computer application. The K-Map is a graphical tool used to simplify a Boolean expression or convert a truth table to its corresponding logic circuit in a simple visual orderly process. Getting familiar with 2, 3, and 4 variable K-Maps. First of all, we're going to look at what a 2 variable K-Map looks like. A 2 variable map, you'd have 2 inputs in your truth table. 2 inputs in your truth table means you use a 2 variable map, and this is what it looks like. There's different ways these maps can be drawn, but this is the map the textbook uses. It's the map that I'm going to use throughout the semester. Notice that we have 4 different states, 4 different cubes. Cube 0, cube 1, cube 2, and cube 3, and they represent your fundamental products and your midterm possibilities. Notice that A is defined by this row here. A bar is defined by this row. B is defined by this column, and B bar is defined by this column. So we have 2 rows, A bar and A, and we have 2 columns, B bar and B. We're going to discuss this in more detail as time goes on. Let's take a look at a 3 variable map. Your 3 variable map is on page 102 in your lecture notes. Three variable maps means your truth table has three inputs. If you have three inputs in your truth table, you use a three variable map to simplify. This is what the map looks like. Notice it has your 8 different subcubes. 0, 1, 2, 3, 4, 5, 6, and 7. Notice the numbering scheme. 0, 1, jump out to the end, 2, 3, and then you come down 4, 5, and then you jump out 6 and back to 7. The reason these subcubes get numbered like this is because in order for this K-map process to simplify these expressions here, it has to be in a form where as you go from one cube to another, only one bit changes. So subcubes that are adjacent to one another, in your representation of them, only one bit changes. In other words, there's a gray code scheme between each subcube. That's very important. That's why it's numbered like this. Here you have a row, which is A bar, and you have a row that's A, and you have two columns here that are B bar. The first two columns are B bar, and the second two columns are B. You have a 4 variable map. If you have 4 inputs on your truth table, you would use a 4 variable map. A 4 variable map looks like this. 4 variable map has 16 states, and there's your 16 subcubes. Let's take a look at the way it's numbered. 0, 1, 2, 3, 4, 5, 6, 7. Just like the 3 variable map. And then we jump down to the last row. 8, 9, 10, 11. Then you come back up. 12, 13, 14, and 15. That's the way the subcubes have to be numbered so that it forms a gray code, and the reduction techniques using these K-maps works. Here, if you take a look, the first 2 rows are A bar, and the last 2 are A. Okay. The 2 middle rows are B, and the 2 outer rows would be B bar. Here, the first 2 columns are C bar, and the last 2 columns are C. And down here, D is the middle 2 columns, and the outer columns here and here are D bar. They're outside of D, so they're D bar. If you notice, when I label these maps, I only show the true variable. I don't show the bar variable. In other words, A here is these 4. B is these 4, and C are the 2 of the middle 4. Down here, A is the last 2 rows, B is the middle 2 rows, C is the last 2 columns, and D is the middle 2 columns. You'll see why we do that as we go through our different problems here. On page 103, using K-maps to simplify Boolean equations. You have to look this page over. I'm going to read it to you real quickly, but then we're going to work some problems here. Using K-maps to simplify Boolean equations. Determine when to use 3, 4, or 5 variable K-maps. It's real easy. A 3 variable K-map when you have 3 inputs, a 4 variable K-map when you have 4 inputs, and a 5 variable K-map when you have 5 inputs. Using K-maps to simplify logic equations. After you write the output expression in midterm form, put a 1 in the corresponding midterm subcube in the K-map. Then you group the 1s into pairs, quads, or octets. In other words, you try to group the 1s that you put in the K-map in groups of 2, in groups of 4, in groups of 8, in groups of 16, has to be powers of 2. You always make the groups as big as possible. Here's the rules and comments for grouping. You're going to have to go over this again once we work some problems. Allowable sizes of groups are powers of 2. 1, 2, 4, 8, 16. To be a valid group, all 1s must be adjacent to each other. That's very important. All the 1s must be adjacent to each other to be a valid group. Always make the groups as large as possible. If you don't make the groups as large as possible, you're not reducing the whole way. Your logic will be accurate, however, it won't be in the simplest form. You have to make the groups as large as possible. Rule midterms when possible. I'll explain that to you. The expression for output x can be simplified by properly combining those squares in the K-map that contains ones. The process for combining these ones is called looping. Looping a pair of adjacent ones eliminates the variable that appears in the complemented and uncomplemented form. We'll explain what I mean by that. And Boolean algebra is being performed when you group the ones and you follow these rules. On page 104, let's go through some quick examples here. First example, y equals AB. In the midterm form, it's a sum of the midterm 3. So I want you to notice there are two inputs, A and B. Okay? You use a two-variable map, and you put a 1 where the 3 midterm subcube is, which is here. The only group you can form is one group. You circle it and you look. It's in A and it's in B. It's in A. A, don't forget, A are these two, and B are these last two. A is the last row and B is the last column. Y equals AB. It's in A and it's in B. Let's look at this example. The OR gate. In the OR gate, this is the truth table. Midterm, the midterms are 1, 2, and 3. Here they are, 1, 2, and 3 for the OR gate. The abbreviated form is y equals the sum of the midterms, 1, 2, and 3. Don't forget, it's a two-variable map we have to use. So you put 1s in the corresponding midterm positions. 1, 2, and you 3. And now you have to do looping here, and notice there's make the groups as big as possible. There's no groups of 4 because this one isn't filled, so you can make two groups of 2. The first one I'm going to circle is this group. This group here is in A. But notice these two ones, when you group them, this one is in the A, and this one is in the A, so you represent the A. However, this one is in B and this one's out of B, so you don't write B on that. You only include the terms that are inclusive or exclusive. Remember this previous, you have to look back here. Remember it says here, looping a pair of 1s eliminates a variable that appears in the complemented and uncomplemented form. That's what I'm talking about, number 6 there. And then this group right here, if you look at it, part of it's in A and part of it's in A bar. So you forget about it. Because we know when you see an A or an A bar, let's write that down here. When you see an A or an A bar, you know that goes to a 1. Okay? So you can forget about it. So this is A or B. Let's look at the next example. If you look back on page 98 of your lecture notes here, we had a design on page 98 of your lecture notes. You can read the specification. And then x was equal to the sum of the midterms 3, 5, 6, and 7. That took 8 gates to implement that. 8 gates. But if you use a 3-variable map, because it has 3 inputs, you need a 3-variable map, and you put one where the 3 is, a one where the 5 is, a one where the 6 is, and one where the 7 is, and you make the groups as big as possible, have 2 groups of 3. 2 groups of 3. If you go through and you look at it, you get an AC or AB or BC. It takes 4 gates, so you simplified that. Take a look at design number 2 on page 99 of your lecture notes. That's the simplified form right there. Y equals the sum of the midterms 3, 7, 11, 12, 13, 14, and 15. It was a 4-variable input. You have to use a 4-variable map. I put 1s where all the midterms are. You don't have to put 0s where the other ones are. That's understood. Now we have to form groups with those 1s as big as possible. You can't form a group of 16. That would be all 1s. You can't even form a group of 8. You can't form a cube of 8 there. It has to be cubes. But here I can form this one right here. And you just go in order. You go in order as you represent these terms. A, they're all in A. B, they're all in B. C, these 2 are in C. These 2 are out of C. Because of this, you can forget about C. And then finally, let's look at D. These 2 are in D. These two are out of D. You can forget about D. So that finishes this loop with AB. How about this one here? A. These two are in A. These two are out of A. Forget about it. B. These two are in B. These two are out of B. Forget about B. C. Every one of these are in C because C is the last two columns. So you write the C down. In D, every one of these are in D because D is the two middle columns. It's CD, and you're finished. I'd like you to look at page 106, and I'd like you to work problems 1 and 2, and then look at page 107 and work problems 3 and 4. Stop the video and try those. When you come back, I'll have the answers for you. Well, hopefully you stop the video, and there's the answers here for example 1. Example 2. Here's the answer for example 2. Example 3. Let me point this out. Notice I could form a group of 4 right here. And I get my W bar Y right here. And then two groups of 2 down here. This group of 2 here gave me my Y. Let's see. It gave me my Y, my W. Forget about X. Y bar, Z bar. Gave me this one out here. And this bottom loop right here gave me my W. X bar, it's out of X. Y bar, it's out of Y, and it's in Z and out of Z, so forget about Z. So there's your expression. And here on the last one, example 4, notice that we can make this group of 4. We took care of these ones, but how do we get these ones down here? Well, you might say, well, gee whiz, that's just a group of 2. Well, don't forget, the reason we numbered these funny is there's only one bit change between this edge and this edge, and this edge and this edge, so I can roll these. I can make a group of 4 by rolling this one, and that becomes these guys right here. That's a group of 4. Okay, and that's this expression. And then I can roll this one with this one with this one with this one. All these 4 corners I can roll to make a group of 4. And that's my B bar, D bar right here on these 4. I'd like you to work on page 108. 108 is homework. I have 1, 2, 3, 4, 5, 6, 7, 8 problems here. I want you to make sure that you can simplify these Boolean expressions by using these K-maps. It's very important before we go into the next video, which is K-map design problems. And that's this lecture.